Welcome to another session of Build and Learn with Chi. Have you ever wondered how the sound from your favorite music, TV shows, or even your best friend's voice actually reaches your ears? In this video, we're breaking it all down, diving into the fascinating world of sound waves. Let's talk a little bit about waves. What are waves? A wave is simply a disturbance that transfers energy. Waves are usually grouped into two main types: transverse or longitudinal. Sound waves are a type of longitudinal waves produced by vibrating objects that travel through a medium. The medium could be air, water, or solid. What it means is if you can get particles to vibrate or distort particles from their original state, and in the presence of a medium such as air particle or water or solid, you will definitely hear sound. The following video shows me disturbing a tuning fork by applying a force or a pressure on one end, and then when the other end is placed on the table, a sound of distinct frequency is generated. For us to fully get the idea behind sound waves, it's best we introduce other scientific concepts and equations that you may be familiar with. Now, why? Because science is just all one big interwoven idea, and everything is related. In referring back to our definition of sound waves, we mentioned that the waves generated has to travel in a medium, and the medium could either be solid, liquid, and gas. So the first concept we're going to reintroduce in is the particulate nature of matter. We know everything is made up of particles and how they are arranged, how much they move, and the amount of energy stored in these particles determines their state. The diagram shows arrangement of particles in solid, liquid, and gas. I'd like you to hold this image and thought in your head. We'll be referring to it to explain how vibration can transfer energy and how this energy would move in these particles. We would also be introducing the formula to calculate work. Work is often defined as force multiplied by distance. Therefore means that when a force is applied to an object or a particle, and then that particle or object moves a certain distance, in simple terms, work has been done. Conversely, energy is also defined as the ability to do work. It means every time work is done, energy of one sort or the other has been transferred. To illustrate, if I apply a force such as a pull or push on a cart, and then I get it to move a certain distance, I have done work. And most times, chemical energy from my muscles would have been transferred to the kinetic energy store of the moving cart. So back to the idea of all matter or medium as the case may be they solid, liquid or gases being made up of particles. We're thus saying that if we apply force to a medium or matter and as a result the particles begin to oscillate either side to side or upwards and downwards or they move any distance at all, we're saying that work is being done and energy is transferred. So the key takeaway is as long as particles move or as long as they are oscillating, even around the central position, the potential energy store of those particles increases. Well, what happens next? Energy is transferred. Have you ever cradled a hot cup of coffee in your palm on a very cold day? What were you hoping to happen? We usually do that because we anticipate that some of the heat energy would be transferred to our palm and then we would feel warm. Well, that's exactly what happens with energy transferred to the particle's kinetic or potential energy store. The energy generated as the objects are vibrating or oscillating are transferred to the next particle and on to the next particle and on to the next. And that's how sound wave travels. But here's the important part. The particles themselves don't travel from your source to your ear. Instead, they oscillate back and forth around a fixed point. It is the energy generated from vibrations or oscillations that travels from one particle to the other. A slinky can be used to illustrate this. Here, I apply some force to one end of my slinky by pulling or pushing, and waves are generated in the direction of propagation. Notice that the individual rings of the slinky does not move. I have held on to one end and I haven't let go. Yet, the wave is able to travel from one end of the length of the slinky to the other end. Notice also that as I pull or push on the slinky, there are areas that appear much more squished together and areas that are spread out. In sound waves, we call these areas of compressions and rarefactions. Compressions are areas where the particles are pushed close together, so there's a lot of pressure in this region. And rarefactions are areas where particles are spread apart, so there's very low pressure in this region. Sound waves basically are a series of repeating pattern of high pressure compression and low pressure rarefactions. These regions move outward from the sound source, carrying energy with them in the same direction in which they were made. That's what we call a longitudinal wave. The particle motion is parallel to the direction the wave travels. We can relate this to everyday activities such as talking or singing your favorite song. Every time we do that, our vocal cords vibrate. This vibration allows work to be done because the particles would have moved a little bit from their rest position. Energy is thus transferred. Energy would further be transferred to the air particles close to your mouth, and then from the air particles close to your mouth to the ones further away, and on and on and on until it gets to our ears. However, the medium itself, in this case, also the air particles close to our mouth, does not move. It is only the energy transferred that moves on from one particle to the other until we hear the sound. But we do not hear all disturbances of vibration. The human ear can only hear sound in certain frequency range, from 20 Hz to like 20,000 Hz. Any other frequency above or below that cannot be heard naturally by the human ear. Now, I just mentioned frequency. To help us explain that, as well as some other key terms associated with waveforms, we're going to be taking a look at a wave diagram. The first we'll be considering is amplitude. Amplitude is simply the maximum displacement of a wave from rest position. It's how high the wave is. And remember our original discussion about energy and work. For a wave to be displaced to a certain height, some work would have been done. How much work tells you how much energy the wave holds. Therefore, amplitude simply tells us how much energy the wave has. The bigger the amplitude, the more energy that wave has, the louder the sound. The smaller the amplitude, usually less energy that wave has, the softer the sound. Think of amplitude as you would a drum. If you hit really hard on a drum, the louder sound you're going to be getting out of it. And then if you go gently on the drum, the lower the sound. Next is frequency. Frequency is simply the number of waves produced in 1 second. It simply tells you the speed with which waves are being generated. A higher frequency means a high pitched sound, like a sharp whistle, for instance. And then a lower frequency means a low pitched sound. Now, let's link what we have learned so far to our project. The particular unit shown on the screen was taken out of a passive speaker and then connected to a signal generator. Notice how the cone vibrates. It pushes the air particles on top of it out, which we have called compression earlier, and simultaneously pulls back or relaxes, and we call that rarefaction. This vibration does generate sound. I've turned off the sound in this video so we concentrate instead on the vibration of the speaker cone for now. And next video would be on electromagnetism and how it can be used to create vibrations. If you like our content, please show support by clicking on the subscribe button below. See you next time.